Hey guys, welcome to our video for 6.2. Today we're going to start looking at polynomial functions and their graphs to sort of give us kind of a preview of where we're headed for the rest of this chapter. You don't need to use graph paper today, we're just going to be sketching. But you should take a moment to set up your note sheet with the section and the I can statement and the date, and then resume whenever you're ready. All right, so the first thing we need to remind ourselves about a little bit is what a polynomial actually is. So I've got a few examples up here of generic polynomials. And the first thing I want to remind you guys about is what a degree is. So remember that the degree is the highest exponent in a polynomial, and if it's written in standard form like it should be, the terms will be in order with decreasing exponents. So then the degree is the exponent on the first term for the variable. So in other words, like for ax plus b, our degree is 1 because x has an exponent of 1. Ax squared plus bx plus c would have a degree of 2. Similarly, the cubic function you see next would have a degree of 3. And then the quartic function, ax to the fourth plus bx cubed plus so on, would have a degree of 4 because the highest exponent is 4, right? The term with the highest exponent has an exponent of 4. The other thing I wanted to remind you about from Algebra 1 are some of the rules about exponents, or about polynomials, I'm sorry. So the first one is that coefficients always have to be real numbers. They don't have to be rational numbers, but they do have to be real numbers. The second rule is that exponents must be non-negative integers. So while their coefficients can be really any rational number, the exponents have to be non-negative integers. We talked about this one already. The degree is the largest power of x, the largest exponent of x. The other thing I want to note about polynomials is that the graph will always be smooth and continuous. In other words, whatever we're graphing will be curves rather than perhaps something that looks more like an absolute value function. The graph will be smooth and continuous throughout. The other reminder is that standard form always has your exponents going from greatest to least as well. So let's just look at a couple examples here together, just to remind ourselves what is and is not a polynomial. And it would be good for you to take a glance at these 5 functions right now and see if you can decide for yourself which ones are polynomials and which ones are not, and then resume the video when you're done with that. Okay, so the first one is not a polynomial. And the reason for that is right here, because it has a negative x in the exponent. So that tells you both that the exponent isn't necessarily positive and it's not necessarily an integer, because x doesn't have to be an integer. The second one is a polynomial. And the reason it is a polynomial is because all the exponents are positive integers, and the coefficients are real numbers. Square root of 2 is irrational, but it is real. So if we wanted to rewrite this in standard form, we would write it as the square root of 2x to the fourth minus x cubed plus 36x squared. Then the next one is not a, so this one is not a polynomial, and that's right here, because x right now is in the denominator, which means if you moved it to the numerator, it would have a negative exponent, which is not part of the definition of a polynomial. The fourth one here is a polynomial, and it's actually already in standard form as well. The fact that pi is in a coefficient doesn't matter, because as long as it's real, it's okay. And then finally, the last one here is not. And again, it's because you've got an x in the exponent, which makes this more of like a quasi-exponential function. But x doesn't necessarily have to be an integer, so therefore it's not guaranteed to be a polynomial. So I wanted to review the kind of definitions of polynomials because our goal is to start looking at the graphs of polynomials. And today we're going to talk a little bit about what's called end behavior for polynomials. And we're going to look at 4 graphs in particular to sort of remind us about this. So I want to graph each one of these on our graphing calculator and then just kind of sketch a picture of it and make a few observations as we're doing it. So the first one here is a fairly simple quadratic. You can probably already picture in your mind what this will look like. So if we graph negative x squared plus 2x plus 4, as you might anticipate, it is an inverted parabola. So I'm just going to kind of sketch this up here just to remind ourselves. So we're looking at a inverted, slightly off-center parabola for that one. So the next one is a cubic function. You may have a sense of this one as well, I'm not sure. So if we graph this one, x to the third plus x squared minus 4x minus 1, what you're going to notice here is that this function looks a little bit different. It has a few turnover points that kind of create bumps on the graph. This one will go on infinitely. So we've got a function that kind of looks like that. Now, the next ones, we're kind of getting into some newer types of polynomials, and this is really the focus of chapter 6 is going to be on polynomials with exponents higher than 2, and often higher than 3. So we've got x to the 4th plus 6x squared minus 5. And if I graph this one, at first you're going to think it looks very much like a parabola. And that's true to some extent, but let's zoom in a little bit here and see if we can see this a little bit more closely. So I'm just going to make my x window a little bit smaller. And what I want you to notice here is if you focus in particular on what appears to be the vertex is in fact somewhat flat. And that's a characteristic of some quartic functions because they no longer simply have just one vertex. So if I sketch this one in here, and we'll look at many different examples of quartic functions as we go, but what I'm going to try to make a note of is that this one looks relatively flat at the bottom of it. And then finally, let's look at the function with an exponent of 5 as well. So we have negative x to the 5th plus x squared plus 1. And I'm going to graph this in the same small window. And if you look at this one, you'll see again that it kind of looks like the cubic function. It's not exactly like the cubic function, but it is certainly quite similar. And the details aren't actually that important for what we're doing today because today what I really want to focus on are the ends of the function, what's called end behavior on the far left and the far right. And just by looking at this, you might notice some patterns already. You might notice that the two functions with even degrees both start and finish either both positive or both negative on the y. And you might notice that the ones with odd degrees start and finish in opposite signs for y. So either positive to negative or negative to positive. So let's look at a table to kind of summarize this information. And let me see if I can make this a little bit bigger for you. So this would be a table that I would like you to add to your notes, or at least, kind of sketches. These are just examples. But what I want you to notice here is if we think about the a value, in other words, the leading coefficient, for even degree polynomials in particular, so we're focusing on even degree here for the left picture. If you notice, if our leading coefficient a is greater than 0, we end up with positive end behavior. In other words, both when you go to the far left and far right, on the x-axis, you end up with positive y values. If a is negative, we end up with negative end behavior in both directions. And this is for even degree polynomials. Now, similarly, if we think about instead our odd degree polynomials, if we have a positive leading coefficient, what you'll notice here is that the negative end behavior, in other words, the end behavior when x is approaching negative infinity, getting very small, you're also going to have negative y values. When x gets very large in a positive direction, you have positive y values as well. And that's true whether it's something like a cubic or something like has a fifth degree. Now, when we have a negative leading coefficient, then it's the opposite. So if a is less than 0, then we're looking specifically where when x is negative, y is positive, and when x is positive, y is negative. And that's true whether we're looking at something that's cubic or something with a fifth degree, seventh degree, whatever it may be. So let's see if we can summarize this information a little bit in a table to finish off this lesson. So when we're thinking about end behavior, and we often call polynomials power functions as well, because they're defined by being raised to a power. But when you think about a simple function like f of x equals ax to the nth degree, you can ignore the rest of the polynomial altogether. And if you think about this question, right, so the degree, the largest exponent controls the shape of the polynomial. If you think about why that is, as x gets larger and larger and larger and approaches infinity, the exponent on x makes a huge difference. For example, if we had ax to the n plus, say, 7x, and imagine that n was the third power even. Once x gets huge, like say a million cubed is going to dramatically outweigh 7 times a million. And that gets progressively more true as x gets larger and larger, either towards positive infinity or negative infinity. So the impact of all the other terms in the polynomial becomes negligible as x gets really, really big. Those other terms have an impact when x is not infinitely large, but as x gets really large, either in the positive or negative direction, all you need to focus on is that first term, which is kind of nice. So if we think about even end behavior, we're basically thinking about the idea that so even end behavior means when the degree is even. And so what we're thinking about here is like ignoring the function altogether. And I want to kind of really drive this point home by, I'm just going to ignore the middle of the function. And I'm just going to put down the end, the arrows, right? So if a is greater than 0 for even degree polynomials, you know that your end behavior is going to go positive in both directions. And if a is less than 0, you know that your end behavior is going to go negative in both directions, ignoring completely the middle of the function, which for this lesson we don't really care about. Now, we're going to use a special kind of notation, what's called end behavior notation, to describe this. And basically what this notation says is, as x approaches infinity, as x gets really, really large, f of x, or in other words, the y values. Now, if a is positive, you can kind of picture that as x approaches infinity, we're looking at this arrow up here, because x is approaching infinity. That tells you that f of x is also approaching infinity. Y is also getting really large. Now, as x approaches negative infinity, when a is positive, we would be looking at this arrow right here. And so our f of x would also approach infinity. And similarly, if we think about our odd end behavior functions, for those ones when a is greater than 0, our odd end behavior function is going to go down as x approaches negative infinity, but up as x approaches positive infinity. And similarly, as a is less than 0, as x approaches negative infinity, our end behavior would actually be positive. And as x approaches positive infinity, our end behavior would be negative. So again, just to talk about the end behavior statements as an example for this, if we think about just when a is positive, just for this example, as x approaches positive infinity, we'd be looking at this arrow, and f of x would also approach positive infinity. But as x approaches negative infinity, f of x, the y, would also approach negative infinity, and we'd end up with that type of end behavior. So you can kind of see here that what we're focusing on for this particular section is just the exterior edges of these polynomial graphs. And we'll focus a lot more on the interior of the polynomial graphs as well later on in this chapter. So that brings us to the end of our video. Please make sure that on your homework you practice writing out these end behavior statements using the notation I showed you here.